as an application, how do we go about finding out how do we apply this heat cooling or the cooling of the heat on everyday life objects? So a very common place that you can find it is in electronic devices. And in electronic devices, over the years, it has developed from not so powerful computing power to more advanced level, like quad-core, high computing power that exists today. So the speed is going to increase, and respectively, the density of the transistor that's inside that processor is also going to increase. So you can see that that transistor is doing switchback. If you are not familiar with transistor, I'll play a very quick video so that you can see what is a transistor.
In this phone, there are nearly 100 million transistors. In this computer, there's over 1 billion. The transistor is in virtually every electronic device we use. TVs, radios, Tamagotchis.
But how does it work? Well, the basic principle is actually incredibly simple. It works just like this switch. So it controls the flow of electric current. It could be off, so you could call that the 0 state, or it could be on, the 1 state. And this is how all of our information is now stored and processed in zeros and ones, little bits of electric current. But unlike this switch, a transistor doesn't have any moving parts, and it also doesn't require a human controller. Furthermore, it can be switched on and off much more quickly than I can flick this switch. And finally, and most importantly, it is incredibly tiny. Well, this is all thanks to the miracle of semiconductors. Or rather, I should say the science of semiconductors. Pure silicon is a semiconductor, which means it conducts electric current better than insulators, but not as well as metals. And this is because an atom of silicon has 4 electrons in its outer shell. This allows it to form bonds with its 4 nearest neighbors. I know that. So it forms a tetrahedral crystal. But since all these electrons are stuck in bonds, few ever get enough energy to escape their bonds and travel through the lattice. So having a small number of mobile charges is what makes silicon a semiconductor. Now this wouldn't be all that useful without a semiconductor's secret weapon, doping. You've probably heard of doping. It's when you inject a foreign substance in order to improve performance. Yeah, it's actually just like that, except on the atomic level. There are 2 types of doping, called N-type and P-type. To make N-type semiconductor, you take pure silicon and inject a small amount of an element with 5 valence electrons, like phosphorus. This is useful because phosphorus is similar enough to silicon that it can fit into the lattice, but it brings with it an extra electron. So this means now the semiconductor has more mobile charges, and so it conducts current better. In P-type doping, an element with only 3 valence electrons is added to the lattice, like boron. And this creates a hole, a place where there should be an electron, but there isn't. But this still increases the conductivity of the semiconductor because electrons can move into it. Now, although it's the electrons that are moving, we like to talk about the holes moving around because there's far fewer of them. Now, since the hole is the lack of an electron, it actually acts as a positive charge. And this is why P-type semiconductor is actually called P-type. The P stands for positive. It's positive charges, these holes, which are moving and conducting the current. Now, it's a common misconception that N-type semiconductors are negatively charged and P-type semiconductors are positively charged. That's not true. They are both neutral because they have the same number of electrons and protons inside them. The N and the P actually just refer to the sign of charge that can move within them. So in N-type, it's negative electrons which can move, and in P-type, it's a positive hole that moves. But they're both neutral. A transistor is made with both N-type and P-type semiconductors. A common configuration has N on the ends with P in the middle.
Just like a switch, a transistor has an electrical contact at each end, and these are called the source and the drain. But instead of a mechanical switch, there is a third electrical contact called the gate, which is insulated from the semiconductor by an oxide layer.
When a transistor is made, the N and P types don't keep to themselves. Electrons actually diffuse from the N type, where there are more of them, into the P type to fill the holes. This creates something called the depletion layer. What's been depleted? Charges that can move. There are no more free electrons in the N type. Why? Because they filled the holes in the P type. Now this makes the P type negative thanks to the added electrons. And this is important because the P type will now repel any electrons that try to come across from the N type. So the depletion layer actually acts as a barrier, preventing the flow of electric current through the transistor. So right now the transistor is off. It's like an open switch. It's in the zero state. To turn it on, you have to apply a small positive voltage to the gate. This attracts the electrons over and overcomes that repulsion from the depletion layer. It actually shrinks the depletion layer so that electrons can move through and form a conducting channel. So the transistor is now on. It's in the one state. This is remarkable because just by exploiting the properties of a crystal, we've been able to create a switch that doesn't have any moving parts, that can be turned on and off very quickly just with a voltage. And most importantly, it can be made tiny. Transistors today are only about 22 nanometers wide, which means they're only about 50 atoms across. But to keep up with Moore's law, they're going to have to keep getting smaller. Moore's law states that every 2 years, the number of transistors on a chip should double. And there is a limit. As those terminals get closer and closer together, quantum effects become important, and electrons can actually tunnel from one side to the other. So you may not be able to make a barrier high enough to stop them from flowing. Now this will be a real problem for the future of transistors, but we'll probably only face that another 10 years down the track. So until then, transistors, the way we know them, are going to keep getting better.
All right, it's a little bit like chemistry, but what you could hear, the overall message is that transistors, they are very small, and they are not a physical switch, but their operation is actually switching. And as you know, when you go about doing switching, you're going to increase its current that's going to, as you switch it, then current is going to flow through. So whenever current is going to flow through into a transistor, the transistor is going to get heated up. And now imagine that our modern day computers, the processors is packed with millions and millions of transistors. That's a lot of heat produced in a very small little tiny area. So that amount of heat that's produced, if I'll bring it into perspective, this is a figure that shows that if you have a rocket, that kind of heat power density is going to be about here, and your Pentium-3 is already here. So you can see that per square area, that amount of heat that's generated is going to be tremendous. The power that's generated by the transistor can be calculated by taking the voltage multiplied by the current. P is for the IV, VI. And this is part that that video is trying to show. You have that transistor here, and if these two sides are tuned to each other, then actually the switch doesn't require a gate over here to turn it on. The job of the gate is to apply a voltage so as to allow electrons to flow through. Electrons flowing through means that the circuit is connected. That switch is closed. So that's the job of the transistor. So you want all this turning, switching on and off rapidly, and this rapid switching on and off will again generate a lot of heat. And that's why thermal management becomes very important, and that's why we are here to transfer. So this chart over here is trying to show you, I know it's very tiny, but it's just trying to show you that the hot port right now is right over here. It has a transistor density of about 1 billion transistors in there. And this axis over here is the year. This one as well is the year. I think you have the high power spot. T3, if you know about computing, that is a very high density processors. And what I want to point out is this very interesting thing. What I want to point out is this thing about silicon. Right? Now, you have seen in the video that he talks about using silicon as our tracks to for the electrical current flow through. Now, silicon has a very unusual behavior. Its unusual behavior is that its electrical resistance increases with temperature. So the higher temperature that this silicon is exposed, its resistance is going to increase. Now, if you think about the Ohm's law, V is equal to IR, whenever I say resistance is increased, how about current? If I have a constant voltage, if I have a constant voltage, if I say that the resistance now increased, how about the current? Will it increase or decrease? The current will increase, right? Because V is equal to IR. If R is going to increase and this is constant, then I is going to increase. So the funny thing about silicon is that under high temperature, its resistance will increase, but there's a limit to that. Until the temperature of 160 degrees Celsius, if you surpass that, what's going to happen is that its resistance is going to drop. Beyond 160 degrees Celsius, the silicon's resistance is going to drop. Now, this is bad news to us, because if resistance of the silicon is going to drop, what does that mean to the current? Current will increase. And increasing the current actually will heat up our transistor. And if it's going to heat up our transistor, the transistor's temperature is going to increase further, and resistance is going to drop further, and resistance is going to drop further, current is going to increase even more, and we have this cyclical, what we call the runaway effect. That is what we call the thermal runaway. So once you have these transistors that are operating beyond 160 degrees Celsius, you will go into a runaway effect, and you will see that there's going to be a breakage at that connection over there. If I were to sketch that 160 degrees Celsius on this axis, this one here is temperature, and this axis over here is mean time to failure. So 160 degrees Celsius is roughly about here. So something like about maybe 4 times 10 to the power 5 hours. 4 times 10 to the power 5 hours, that's roughly about maybe close to 10 to the power 5 over here is 11 years. 10 to the power 6 over here, that is 114 years. Or somewhere in between. So you can see that that's why we can't use silicon as long as we keep that temperature to be manageable at less than 160 degrees Celsius. If it's more than 160 degrees Celsius, it's going to run into a thermal runaway, and then it's going to break down. So that's where our heat transfer knowledge comes in, that we're trying to cool down that transistor to make sure that it's below 160 degrees Celsius. Now, this part here is a microprocessor. The funny thing about microprocessor is that you don't get uniform heating across the entire microprocessor. What's going to happen is that this is going to be a very localized heating, and localized heating on a computer board is not a good news. Why is not a good news? Because that means that area has a very high concentration of heat. gets a very high concentration of heat, then it's likely that you will burn through something's going to fail out. So what we normally do is that make sure that the board can tolerate different temperatures. So you'll be able to see this the thermal image of this computer board, and that thermal image suggests that there are few spots, this, and that's going to be heated up. That's heating up, and you will want to build the PCB board over there to be able to withstand that higher temperature concentration. So that will save up some of your materials cost. I think that's a repeat of the heat, so you just need to control that out. So if that localized temperature is going to get too hot, we need to put in something, and if you play with your audio equipment, you would be seeing these heat sinks very frequently. What the heat sink does is to transfer the heat into these cooling fins, and then you have this fan over here to suck out the air so that you can experience forced convection. And the forced convection is going to cool down these cooling fins so that the heat from the bottom part of it, which is your microprocessor, will be transferred out and then into the environment so as to lower down the surface temperature of that microprocessor. Why we want to do that? That's because if we don't cool it down, then it's going to run into a thermal runaway. The design of the heat sink is such that you will pull in the cool air, and then you will interact with the cooling fins, and then you will discharge that hotter air into the environment. The material of the fins, the surface of the fins, surface property of the fins, the air velocity, all these plays a role in how good is that cooling fin is designed. For the practical heat sinks, for these electronic devices, it must have a temperature that's higher than the surroundings. So if you implement these cooling fins, some students, actually my FYP students, when they were doing the cooling fins, something very interesting came up. So they were wondering that if I were to have a surface that I want to cool down, and this surface is at, say, about 35 degrees Celsius. Now, 35 degrees Celsius is higher than the ambient temperature. So we can assume ambient temperature to be about 30 degrees Celsius. So you was wondering, hey, I have 35 degrees Celsius on the surface that I want to cool down. The ambient is 30 degrees Celsius. Can I put a cooling fin right on top of it, hoping that that 35 degrees Celsius will be cooled down to 30 degrees Celsius? The answer is not. You're not going to achieve a good heat transfer. Why is that so? Because in order for your cooling fin to work, you must have a huge difference between the ambient temperature and your cooling fins. And how can your cooling fins get to be at a very high temperature? That's when your source temperature is high as well, so that high source temperature could be conducted to your cooling fins. And hence your cooling fins now is hotter than the environment, so that heat can get transferred out. Might it be through natural convection or forced convection? Right? So you need to have that source temperature that's really a lot more hot compared to the environment before you can have effective cooling. And something interesting also popped up in this final year project. So he was also wondering, okay, now I have something of a higher heat source temperature. I'll just plug in my cooling fins. Why is it still not really cooling down my heated surface that well? That's because microscopically, when you put that cooling fins on top of the surface that you want to cool down, say for example, metallic surface, your cooling fin is also made of metal. The metal to metal contact is going to look something like that. there's going to be air gaps in between. So now the question is that these air gaps would actually have a thermal conductivity that's a lot more lower conductivity of air, thermal conductivity of air. It's actually a lot more lower than the thermal conductivity of solid. So if I have, say, for example, these points here, they are in contact, that surface area is actually a lot more smaller than this entire surface area, where it's insulated by that small little column of air. Now what that means is that instead of having air over there, we need to put in something to fill up that air gap so that we could have a better conduction from one surface, solid surface, to the other solid surface. This kind of material is what we call thermal interface material, or in the industry we call it TIM. So TIM, sometimes in the layman word, you get to hear thermal grease, and it's kind of, it looks something like toothpaste, white color. There's some that comes in a little bit silvery color or grayish color. That's because they impregnated with a lot of metallic foulings in there, so that these foulings would be a good conductor to fill in the air gap that exists between the two solid surfaces. So it's important to take care of that. The air thermal conductivity is 0.022, whereas TIM's is 0.3. So you can see that there's a great improvement in thermal conductivity if you fill in those small little air gaps with TIMs. But even though if you fill in those gaps with TIM, you're still going to be facing what we call interface resistance. So we could imagine that now those air gaps are filled in with TIMs. Now the fact that is from one solid object, solid surface to TIM to another solid surface, that interface over here will give you what we call interface resistance. Resistance, thermal resistance is bad news for us. Why is it bad news? Because isn't the job of a cooling fin to cool down that surface? If I have resistance coming in as interface resistance, that resistance is going to impede my heat from flowing to my cooling fins. So those resistances, the more you have, the bad news it will be for us in terms of cooling down or encouraging heat transfer. Now heat sinks, there are different kind of materials. Mostly you could see they are aluminum alloys. You get more exotic ones. For example, Dimaloy. Dimaloy is diamond in copper silver alloy matrix. And as you have heard before, diamond is going to give you the thermal conductivity that's about 2,000 watts per meter Kelvin. 2,000. So even for metals like copper, it's only about 200 to 300 watts per meter Kelvin. So diamond is really good form of material to use. Obviously, we don't use pure diamond for our cooling fins. We can't find like a diamond cooling fins around, although they are the best. What we could find are composite materials or synthetic diamonds. And usually those are for the cases of high power IC circuits, or in the case of a laser, those high power lasers, you would want to use synthetic diamond as your cooling fins to conduct the heat away. So it sounds like for heat sink, we need to have high thermal conductivity, and there's also another property which is called heat spreading characteristic. So I'll be talking a little bit more about heat spreading characteristic in a couple of slides later. Let's have a look at the fin efficiency. Now the fin efficiency, what it means is that if you take the ratio of actual heat transferred, divide that by the heat that will be transferred if the entire fin will be at base temperature. What does that mean? I'm going to do a sketch of a cooling fin. And I'm going to sketch out a temperature profile inside the cooling fin. The kind of temperature profile that you're going to get is going to look like a grid shape. It's going to look something of this nature. Symmetrical. Now what I want to show you is that, okay, this part here, the tip will be insulated. What I want to show you is that this part is called the root of the fin. The root of the fin temperature is not going to be the same temperature as the rest of the part of the fin. So what that means is that if you put the cooling fin onto a microprocessor, you'll find that the part that's nearer to the microprocessor will be at a higher temperature compared to the other parts of the fins. That's because the heat that's flowing out into the is going to diffuse to where it's nearest to the ambient. It's not going to make its way all the way to the end of the tip. You will try to get cooled down somewhere over here because that's the nearest part for cooling. And what that means is that the temperature within that cooling fin is not going to be constant. If it were to be constant, that will be an ideal cooling fin. Why would that be ideal? That's because now I'm able to cool down this surface on the left-hand side using a cooling fin that can really achieve the same temperature as the root throughout the entire cooling fin. This is ideal. The one that I sketched over here is the practical case. Practically, you're going to have this lower part here that's at a higher temperature and the tip over here that's at a lower temperature because heat couldn't get transferred all the way to the end of it because there's certain thermal conductivity. If you use diamond, then yes, more heat can get to the end of it. So that's the definition of what do we mean by the fin efficiency. Actual heat that's transferred divided by the heat that would be transferred if the entire fin would be at the base temperature. Right? So this base temperature refers to this base over here. So that would be the base. And we know that this base temperature in real life will be higher than this temperature over here. So it's the base temperature, T base, T tip. T base will be at a higher temperature than T tip. That's what you will find in real life. If base temperature is equal to T tip, that means that will be equal to the actual heat transfer, and you get 100% heat efficiency. That's what it's trying to say. And there are this set of equations for your fins. So we start by looking at this. MLC. MLC, if you were to find it out, you'll be substituting it into this equation that allows you to find out what is the fin efficiency. So for MLC, it's dependent on HF, which is the convection coefficient of the fin. So for the air, it's this value. For water, it's that value. K here refers to the thermal conductivity of the fin. So for aluminum, it's around this value. LF over here refers to the fin height, and TF here refers to the fin thickness. So the fin height and fin thickness refers to the following. This will be the fin height, and that will be the fin thickness. Now there's one last thing that I want to talk about, that is your spreading resistance. Okay, I'm going to zoom in over there. Now this part also came out as one of the past year questions when you talk about the spreading resistance. So spreading resistance is defined as the thermal energy that is transferred from a small area to a larger area. That's why it's spreading resistance. So in a heat sink, what that means is that the heat does not distribute uniformly, just because that is spread out now. It's not spread out uniformly with respect to the base of that. So the spreading resistance phenomenon is shown by how heat travels from the heat source location and cause a large temperature gradient between the heat source and the edge of the heat sink. So whenever your heat sink can afford a large temperature difference, it's desirable for this spreading resistance, because now if there's a huge temperature difference, then heat can flow out. So that's the meaning of that. So in order to decrease the spreading resistance, since resistance can adjust, we can increase the base thickness, or we choose a different material, or we use what we call the heat pipe. Now, heat pipe will be covered in the later part of your lecture. Toward the end of the course, there will be some advanced topics, and we'll be talking a little bit about what heat pipe is. If you look into a computer, they actually don't use forced convection to blow over the processor. They also don't implement on top of the microprocessor. They don't implement a heat sink up there. They don't put a heat sink on top of it.